Okay, let's start. Now I would like to explain the previous in-class report. Uh, so I have returned the graded result by email, like that. So please check them. They should have been sent to the email address you used when submitting the in-class report. You should have received an email in this format. As feedback, I have included explanations. So I should say, like that. So as feedback, I have included explanations whether your answers were correct or incorrect. So please refer to these. Let me explain the first problem, which asked whether there is a clear definition of what AI is. Their answer can be found on page 11 of the lecture slides. There is no clear definition. Definitions can differ depending on the person or book, so this requires attention. Okay, the question about when the first AI boom started is answered on page 36. It began in the 1950s. For the third question, in model selection for machine learning, choose the most appropriate explanation from the following. So, Occam's razor states if predictive accuracy is the same, adopt the representation with simpler knowledge. While the no freelance theorem states there fundamental cannot exist a learning method that always performs well for all any learning target. Therefore, the first option is correct answer. The first option is incorrect because it states more complex model because the more its predictive accuracy improves. The second option is completely opposite to the correct explanation. Now, the third option is also wrong because it states as models become more complex, the risk of overfitting decreases. Okay, next. Let's look at the question asking for the most appropriate explanation among supervised learning, unsupervised learning, and reinforcement learning in machine learning. The first option is correct. The second option describes reinforcement learning. The third option describes the supervised learning. The fourth option also describes the supervised learning. Since these differ from the actual definitions, options 2 through 4 are incorrect. The last problem uh, asks you to choose the number obtained when executing a specific code in Google Collaboratory. Let's check how to do this. Okay. Okay. First open Google Collaboratory. When you want to write code yourself, as I mentioned before, you write the code in the code cell. So code cell here. If you want to add a new code cell in the middle, place your cursor where uh, you want to insert it. Then plus code button will appear like that, which you can click to create a new code cell like that. Okay, so please copy, copy, and paste the code from the program into this cell. Once pasted, press the execute button. Okay, so let's execute. Since this is the first execution, you will see connecting in the top right. After waiting a while, you will see something like 3.1415, which is an approximation of pi. This code is what's called Leibniz method, an algorithm that can approximate pi. Therefore, the answer is approximately 3.1416. If you are having trouble with this operation, please contact me by email or Teams and say I need help. If you can't do this, you will have difficulty in future classes, so please make sure you can execute code properly. Okay, now let's move on to the explanation of the second in-class report. Okay. Uh, okay. Since Python indexing starts from 0, in the list numbers, the zeroth element is 1. The first element is 2. The second element is 3. To output 3, we need to access the second element. So the correct answer is to put in 2 in place of A. So let's actually check this. One of the good things about programming problem is that we can try them out. Okay, so let's copy. Oh. And paste. And we put 2 in place of A. And run the code. We indeed get 3 as the output. Okay, so let's go next question. Okay, the question asks what will be printed when the following code is run. We have n assigned value 5, followed by a condition statement that prints positive if n is greater than 0, and negative if n is less than 0. Since n is 5, which is greater than 0, the first condition of if statement is satisfied, and positive is printed. Okay, so we can confirm it, and copy and paste. So then execute. Okay, obtain the positive as output. Okay, next. Hey, the question asks, what should you put in place of B to make hello printed three times? In this code, range B determines how many times for the for loop executes. To output hello three times, we need to set B to 3. Okay, copy and paste. Okay, B. So we set 3. Okay. So we can verify this by running the code with bset3, which results in hello being printed 3 times. Okay, next. The question asks how many times will hello be printed by the following code. The variable counts out to 0, and the while loop continues as long as count is less than or equal to 3. Let's trace through the execute step by step using Python tutor. Okay, let's copy, copy, okay. Okay, so initially count is 0, like that. So since 0 is less than or equals to 3, the loop execute and hello printed. Count becomes 1. So look at here. Uh, count becomes 1. Since 1 is less than or equal to 3, the loop execute again and hello is printed. Count becomes 3 since 2 is less than or equal to 3. The loop execute again and hello is printed. Count becomes 3. Since 3 is less than or equal to 3, the loop executes again and hello is printed. Count becomes 4. Since 4 is not less than or equal to 3, the loop terminates. So hello is printed 4 times in total. Like that. This is a bit of a tricky question. There was similar code in the distribute materials, but that used const is less than 3. So this part is count is less than 3 instead of count is less than or equal to 3. This one character difference changes the number of execution by 1. Uh, with count is less than 3, the loop would exit when count reaches 3. But with count is less than or equal to 3, the loop also executes when count is 3, adding one more execution. Okay, let's back. The question asks use the least square method to estimate the parameters of the simple regression model using Python. Let's actually do this. First, I will copy the problem data and paste. The method, the method to calculate the regulation using the least square method was covered in the second lecture material. Zero two linear regression. Okay, let's go. Okay, here. The process involves preparing the data, calculating the means, determining beta 0 and beta y using variance and covariance, and outputting the results. Since the data is given, we can use that code. So this code. Okay, so we copy and add the following to the end of the code using class. Oh, so we need to write import numpy as np at beginning to use the np library. This makes NumPy available to us. When we run it, we get a slope. Okay, run. Okay, we get a slope of 1 and y-intercept of approximately 4. And therefore, correct answer is slope of 1 and y-intercept of 4 here. Some of you might have struggled with this problem, but it could actually be solved by just changing the data portion. Last question. Ask to calculate the slope and y-intercept of the regression line for these three data points manually. The steps for manual calculation are the follow here. Calculate the mean of x, so 1 plus 2 plus 3 is 6. 6 over 3 is 2. Calculate the mean of y is minus 1. The variance for x is 2 over 3, and the covariance is minus of 4 over 3. Therefore, the slope beta 1 equals minus 2. So beta 1 is covariance over variance, so minus 2. And beta 0, so y-intercept is mean of y minus beta 1 or times mean of x. So minus 1 minus 2 times 2. So y-intercept is 3. That concludes the explanation. Okay. Now, let's address some questions that were asked in this comment. Okay, so first question is here. I'm not sure if overfitting will be covered in future classes, but I would like an explanation and want to know how to improve overfitting. As I mentioned in class, overfitting is a phenomenon where a model performs very well on training data, but has large errors on unknown data. So training data. When a model fits the training data too well, its ability to handle new data decreases. There are several ways to prevent overfitting. For example, you can use regularization to control the complexity of the model. Also, while having more parameters increases a model's expressiveness, it also increases the risk of overfitting. In such cases, you can use careful cross validation to estimate the uh, approximate number of parameters. This will be explained the detail in the nearest neighbor lecture, so lecture 5, so fifth lecture. Okay, let's go next question. Here. I have a question regarding the calculation of variance and covariance in. I noticed that the case in class, the formulas divided by n rather than n minus 1. I was wondering why we don't apply the Bessel's correction to obtain an unbiased estimator. Is blah blah blah. So we can use its approach. Uh, So when calculating beta 1, uh, we divided covariance by covariance. So the 1 over n minus 1 terms cancel out. Therefore, whether you use n minus 1 or n, the final answer is the same. So either is fine. Okay, so next one. So question 3. Okay, so are the content of ChatGPT and the other LLMs determined by language? For example, would asking about French cuisine in French produce more accurate result? More generally, does asking or interesting in instructing in English, which is likely to have more data, lead to better accuracy and quality in responses? Oh, very nice question. You're right. Large language models like ChatGPT are trained primarily on language with abundant information on the internet, so using those languages might yield higher accuracy and responsiveness. In earlier versions of ChatGPT, English response were noticeable better, but now natural responses are available in many languages, including Japanese. For practical purposes, the difference seems minimal nowadays. This is my personal observation. Of course, this applies to ChatGPT. Lower performance models might still show differences. Also, a model called ChatGPT-o1 was recently developed, which allows observation of internet processing that it knows O3. In ChatGPT-o1, you could see that the internal processing makes English, Japanese, Chinese, and as long as it's so, even if you ask a question in Japanese, internally it might be thinking in English or Chinese. In other words, it might be automatically converting the appropriate language internally. Okay, so next question. Yeah. Okay, so in K4, the cross validation, if we divide two 20 data points into three folds, how should we handle the leftover two data points? These answers are also, it's okay, sorry. So you should divide the data as evenly as possible. For example, with 20 data points, you could divide them into groups of 6, 7, and 7. That's all. These answers are also uploaded to Google Drive, so please check there if you want to review them at your leisure. I will continue to answer questions like this, so please don't hesitate to ask. What you don't understand is often what of other students don't understand as well. Even if you think this question might be trivial, don't hesitate to ask. Okay, now let's move on to the lecture content. Okay. Oh. Oh. Okay. Let's start. Today I will talk about multiple regression, multiple linear regression. First, we will First, we will review simple regression. And then I will introduce what multiple linear regression is. We will also check how parameters in the least squares method are determined. I would also like to introduce the coefficient of determination as one way to evaluate regression analysis. Okay, let's start with a review. First, what was linear regression? It was a way to express data trends with a simple formula, specifically to approximate with straight line or planes, like that. By using this, we can make a prediction for unknown data. We can also understand the features of the data itself. For example, in spring experiments, we can find the relationship between weight and spring extension. For rent prediction, we can predict rent from the size of the house, distance from the station, and building age. For sale prediction, we can predict say we may be able to predict the sales from temperature and data day of the week. Okay, so what we wanted to do with simple linear regression was to approximate data with straight line. Specifically, when we have many data pairs like x1, y1, x2, y2, xn, yn, we want to find beta 0 and beta 1 so that beta 0 plus beta 1 x1 is close to y1 and beta 0 plus beta 1 xn is close to yn. For example, if we have data like in this figure, we want to draw a line along this data and find its y-intercept and slope. When we have only two data points, we can determine the line by solving a system of linear equations. But when we have multiple data points, it is usually impossible to draw a line that passes through all data points exactly. So we need to find beta 0 and beta y that make the deviation as small as possible. Uh, For this, we often use least square method here. Specifically, we calculate the sum of the square of the difference between the observed values and predict values, and find the values that minimize the sum. To find the minimum of a function with two variables, we need to find where the partial differential derivative with respect to both variables equals zero. This is granted by the proportional shown here. Uh, by solving these equations, we can express the y-intercept and the slope of the regression line using the mean, variance, and covariance, as we discussed last time. Now let's move on to today's new topic. Okay. As I mentioned earlier, when xi is determined, when we can approximately y1 yi using beta 0 plus beta 1 xi. Here, xi is called the explanatory variable, and yi is called the objective variable. Explanatory variables are variables that are thought to influence the result in the model under consideration. They are also called independent variables or features, and are used to predict or explain the result in the model. The object variable is the variable of the result that we are trying to predict or explain. It's also called dependent variable. For example, when considering a model to predict house prices, the size, the age, and the location would be explanatory variables. Based on these variables, the price of the house is predicted. In this case, the house price is objective variable. Like in the house price prediction model example, we also want to handle linear regression when there are multiple explanatory variables. This is called multiple linear regression. What we discussed last time was regression with a single explanatory variable, which is called simple regression. In other words, linear regression includes both simple regression and multiple regression. So, we want to do in multiple regression is as follows. Suppose we have a data set like x11, x12, x1p, y1, uh, x21, x22, x2p, y2, and so on. In this case, we want to find numbers beta 0, beta 1, blah blah blah, beta p that allow for approximation as shown in this formula. In simple regression, we approximated with line, but for p equals to 2, meaning there are two explanation variables, we approximate with a plane. For p equals 3 or more, meaning there are 3 or more explanatory variable, we approximate with p-dimensional hyperplane. How do we determine beta 0 through beta p? We will use the least square method again. The process is the same as in simple regression. We find variables, minimize the sum of the square of the uh, a difference between the observed values and predicted value. Here, the predict value can be written beta 0 plus beta 1 xy plus beta p xp. So we want to find beta 0, beta 1, beta p that minimize this error. We need to find where the partial derivative equals 0, so let's calculate the partial derivative. But now, the time is so around 14 minutes. So let's take a break here. Okay, let's start. So let's walk through the, this calculation. Let's calculate this in detail. Okay. よいしょ。Okay. よいしょ。So L can be like this. L beta 0. No, no, no. Beta 1, xi1 minus beta p xip square. So, let's calculate the partial derivative. First, for the first partial derivative with respect to beta 0, since so the is beta 0, beta p hat. So since we have the square here, we get factor 2. Two. And since we have minus beta 0 here, so we get a factor of minus 1, so minus here. So we get minus 2 times yi minus beta 0, beta 1, x 1. xip with hat. For the so the derivative with respect to beta 1, beta 0. We again get the factor of 2 because of the square, this square. And since beta 1 has a factor of minus xi1, so we get minus 2xi1. This is same. Yes. So like that. For the derivative with respect to beta p is same with beta 1. So I copy here. So beta, this is beta p, then this corresponds here. Okay, so the derivative with respect to beta p follows the same pattern. This is difficult to handle as it is, so let's define. Okay, let's copy. Okay. Okay, so let's define a matrix X and vectors Y and beta. Define X is so 1 X 1 X1 P X2 1 X2 P Xn1 Xn P. So this part is correspond to first data. This part is correspond to second data. So this part is correspond to first explanatory variable. So this is x is n by p plus 1 matrix. Y is なんだっけ Y is well, objective variable. Objective variables y1 to yn. So this is n-dimensional vector. beta hat is beta 1 hat 2 beta p hat, uh, so beta 0. So RP. So now, so let's rewrite the area partial derivative with using x, y, and beta. Uh, so, we can interpret that beta 0 has a factor of xi0 here, so xi0. So xi0, so this part is j equals 0, this part is j equals 1, so this one is j equal p. So xi0 is equal to 1. So this part is 1. So this correspond to j equals 0 and j equals 1. So xi0 equals 1. Xi small xiy uh, can be written as capital XIY. So XIP can be written as capital XIP. So using some notations, and I minus 1 minus 2 times 1 yi minus p xij beta j hat. Using some notation, we get xij beta j hat by changing the other of multiplication. And then the partial derivative with respect to beta 1 and the other parameter can be written in the same way. So this part is same. So same. Mm, we have this small x. Oh, sorry. So we have this small x here, but we're writing it with capital X. This becomes xi1. So this becomes xip. So Here, there is no x here, but if we think of this as having a factor of y, it can be seen as having a factor of capital Xi0. So, arranging these vertically, since all terms we have factor -2, we can factor out -2. And write everything in terms of xy and y and beta like this. Here, the ith element of y equals x beta is calculated like this. yi equals 0 to p xij part. So this part is same. So this part becomes same here. So this part is ith component of y equals x beta. On the other hand, this can be seen as a transpose of x. So it can be seen and so xi is equal to transpose to 0i. This part is transpose to yi, p, pi. So it can be seen as the transpose multiplied by y x beta hat. So when this equals zero, we have xty minus xtx beta hat is equal to 0. So so xtx beta is equal to xty. Therefore, when xtx has an inverse, we can multiply both sides by the inverse of xtx, and we get beta hat is equal to xtx inverse xty, which minimizes L. So the algorithms for the least square method for multiple regression looks like this. When data is given like this, we consider a matrix where the explanatory variables are arranged vertically with the first column consisting of all ones. We call this matrix X. And if we define the vector y, the objective variable arranged vertically, then we can calculate beta xtx inverse xty to find the regression parameter for multiple regression. In Python, using NumPy, which provides various ways to handle matrices, we can write to it like this. Here, no, here. You may have noticed and wondered, does Does XTX really have inverse matrix? As a condition for this, it is known that when the rank of X is P plus 1, it has an inverse matrix. On the other hand, when the rank of X is less than P plus 1, it is known that it does not have an inverse matrix. Specifically, this can happen when the number of data points is less than p plus 1, or when some columns can be expressed by other columns. For example, when some column is scalar multiply of a column of all ones. Uh, okay. Now let's change the topic a bit and talk about evaluation methods for regression analysis. Suppose we apply the least square method to scatter plot like this, and obtain a line like this. But we might wonder if this can really be called a good approximation. In fact, linear regression calculation can be performed on almost any data. However, just because we can calculate it doesn't mean the approximation is good. So I would like to introduce the coefficient of determination as one measure for evaluating the goodness of a feature model. The coefficient of determination is defined like this. So R square is defined by 1 minus sum of square of difference between observed and predict variables over sum of square of difference between observed value and their mean. Here, yi is observed value, y bar is its mean, and fxi is the predicted value. For linear regression obtained by the least square method, it is known that this coefficient of definition is between 0 and y. When the difference between the observed value and the predicted value is small for all I, the numerator becomes small and approaches zero, so the coefficient of determination approaches 1. On the other hand, with the approximation performance is poor, the mean square error becomes large, so the coefficient of determination approaches zero. Also, also particular when p is equal to 1, meaning there is only one exponent variable. This coefficient of determination can be rewritten as square of correlation coefficient. So it is a number related to the correlation coefficient. Looking at the coefficient of determination for the data looked a random area, we see it is 0.005, which is a small number. On the other hand, the coefficient of determination for data that is close to nice straight line, like the one I introduced at the beginning is 0.8, which is close to 1. There are other points to be careful about besides the fact that linear regression can be applied to more data. Whereas the explanatory variable can really explain the objective variable is a separate question. Even though they are called explanatory variable, whether they can truly explain anything is a different matter. Regression can be applied to most data, but it may not approximate as expected. So it is important to check the coefficient of determination and to actually plot the data. Having a high coefficient of determination does not necessarily mean that the data is well approximated. The regression might also be affected by outlier. For example, if the data is given like this, the regression line looks like this. But if we add just one point, the regression line changes significantly like this. In this sense, linear regression is easily affected by outlier. Another issue is that our method cannot determine whether there is a causal relationship. That is, we cannot tell us whether the explanatory variable causes the objective variable. A famous example is the claim that increased chocolate consumption leads to more Nobel Prize winners. There is a figure protein, so okay. There is a figure plotting chocolate consumption and the number of Nobel Prize. Uh, so Nobel Prize winner per 10 million populations uh, by country, which shows countries with higher chocolate consumption tend to have more Nobel Prize winner. So the coefficient of determination is high. But does eating chocolate increase the number of Nobel Prize winners? That's not necessarily the case. This is what I mean by causality being a separate issue. Because of these issues, we need to consider why linear regression worked well when it does work well. Of course, we also need to consider why it didn't work well when it doesn't. Understanding the data subject itself is important for exploring these reasons. So in this machine learning course, we teach methods like how to handle data and machine learning techniques, but understanding what the results mean require specialized knowledge of the subject. For example, if some result are obtained about ocean graphic data, you cannot interpret those results without knowledge of ocean graphy. If it's about SIP, you need to understand SIPs. If you don't properly understand that part, even if you can perform data analysis, the results you obtain will be incomplete. Also, there is a problem. There is the problem of multicollinearity, which we will discuss next lecture, but not uh, next lecture. So there are various points to be careful about when using a linear regression. Okay. So next let's look at the code specifically, but let's take a break. Mm, Okay, let's restart. Let me explain the code in detail. So today I will use 03 multiple linear regression. Okay. Since you may not be familiar with NumPy yet, I will explain it including some overlap with previous material. NumPy is a library that allows us to efficiently and easily calculate with matrices and vectors. To use it, we must first write import NumPy as NP. Here. Let's execute this. Okay, execute. And it's now. Okay, it's connected. Okay, when we want to create an array, we write np.array followed by a list. For matrices, we write them in this format. We don't need to define and split like list separately. So, plus code, symbol. This is same, so we can define them directly like this. In this notation, each row is enclosed in brackets, with the first bracket correspond to the first row, so this first row. The next bracket to the second row, and so on. When we so so and when we start to we want to create arrays with all element being 0 or 1, we use zeros or for arrays of all zeros and ones for arrays for all ones. When creating arrays for 1D arrays, we simply list numbers in brackets. And for 2D layers, writing like this create 3 times 4 array or field with just ones, like this. As you work with arrays, you might forget their size. In such cases, you can use, uh, for example, checking the shape of this array tell us it's uh, 2 rows, 3 columns. To check how many dimensions an array has, the dimension number use ndim. To find the total number of elements, use the size. In this case, there are six elements, so it returns six. You can also change the shape of created array using reshape. In today's class, we will also use a mention method to uh, con composition column stack. So in today's class, we will also use methods to concatenate matrices. One method is column stack. For 1D array, it arranges them. So for example, so this one. So for 1D arrays, it arranges them uh, column vectors side by side to create a 2D array. For example, if array A is 1 to 3 and array B is 4, 5, 6, then np.column stack A can be will create an array where 1, 2, 3 is arranged vertically and 4, 5, 6 is also arranged vertically side by side. If we perform this on 2D array instead, for example, with arrays C and D, np.column stack C comma D, and place C on the left and D on the right. Since column in column stack refer to columns. They are arranged horizontally in the column direction, resulting in horizontal concatenation. Sometimes we want to specify the direction. In such cases, we can use concatenate to specify the direction for a join. The value of axis might be confusing, so let me explain. Array in detail. When you want to see the content of an array, so this one, so copy. So 0, comma 0. You can specify it like row is row 0, column 0 to get the number at that position. Axis is 0, this one. So axis is 0 means extending in the direction where the first index, so zeroth index, row number increases. So yeah. So C00 is here. C10 is here. So concatenating with axis is 0 means they will be arranged vertically. In fact, we define C 1, 2, 3, 4, D is 5, 6, 7, 8, then NP dot concatenate C comma D, axis is 0, then we obtain these matrices. For 1D arrays, it might look a bit strange, but a zero, so A is here. A zero is here, a one is here. So extending with axis is zero means stretching in the direction where 1, 2, 3 is arranged. So indeed like that. In other words, it's simply concatenating in one dimension. When concatenating to the array with axis is zero, like this, the result looks like this. For axis is one, uh, since 1D arrays don't have a second, second index, so you can't concatenate with axis is zero. For 2D arrays, since C00 is over here, since 0y is here, so axis 1 means extending horizontally. Therefore, concatenating with axis is 1 extend to the right of the row. Please check this carefully later. It doesn't come up directly today, but remember that these future features exist. Okay. Now let me explain how to reference indices. And this is related to what we discussed earlier, so maybe I should have explained this first. When you want to reference an index, for example, to see the zeros index, since indices start from zero, you can get that zeroth element or by writing zero inside square brackets. For 2D array, you write it like this. You can get the element at row 0, column 0, which would be 1 in this case. And you can also extract the number at row 1, column 2, so 6. So since the first row is number 0 to 0, 0, 1, 2, so this would be 6 here. So this would return 6. There are also slicing features using colon here. You can take from the zeroth element up to, but not including the second, meaning from 0 to 1 and from colon 1 to 2. If you omit the endpoint, start point and end point, you can get everything. This would retrieve the entire first row like this. So this corresponds to first row. You can also define arrays with 3 or more dimensions. The notation is the same, but the number of dimensions specified by commas increases. Let me also explain addition and multiplication. As I mentioned last time, addition is uh, element by element addition, and multiplication is element by element multiplication. Uh, there is also a feature calling broadcasting. Normally, calculation can only be performed between arrows of the same shape, but multiplication with scalar is also possible for arrays. In that case, it's automatically expanded to each element. For example, when multiplying array by 20, each element is multiplied by 20, so 10 becomes 200, 20 becomes 400, so and 30 becomes 600. Subtracting works similarly. This can also be applied to 2D arrays. Let's say we have array 1, 2, 3, and 4, 5, 6. When define this, you can use line bucket it to make it clearly. If we add a 1D array 10, 20, 30 to this, what happens is that the 1D array is broadcast in row direction. And that means adding 10, 20, 30 to the first row gives 11, 22, 33, and also adding 10, 20, 30 to second row. Uh, okay. Vector operations are also possible with dot product. Calculate using np dot dot. Matrix multiplication uh, staple of matrix comparison can also be performed like this. Since using asterisk results in element-wise multiplication, we use uh, atmark for matrix multiplication. Transpose is also possible when transposing using dot .t. For example, if we have matrix with 1, 2, 3, and 4, 5, 6, using a dot .t swaps the row and columns to create a matrix with 1, 4, 2, 5, 3, 6. 2 times 3 matrix becomes 3 times 2 matrix. You can also calculate inverse matrix in just one line. You might remember struggling with this in linear algebra class, but in Python you can write it in just one line. You use INV, which is a short for inverse, using a function np.linear algebra.inverse, you can calculate the inverse matrix. If actually multiply the inverse matrix inv by original matrix A, we get approximately the matrix 1, 0, 0, 1. This is what we call identity matrix. Here we see the value of 8.88 e minus 16, which means 8.88 times 10 to the power of minus 16. You might think this isn't zero, but this is due to computational error. A computer cannot store a number like 1.5 exactly. This is because internally numbers are represented in binary. When expressing 1.5 in binary, it becomes a recurring decimal, and even with plenty of memory, it cannot be stored perfectly. Therefore, you have to cut off at some digit limit in memory. Because the original number is truncated as some digit, errors occur at that point. So it's common for inverse matrix calculations and multiplication to not result in perfect integers. Getting back to our topic, determinate, determinants can also be calculated. You can write this here using the det, which is short for determinant. Let's calculate the determinant of the matrix 1, 2, 3, 4. It's 1 times 4 minus 2 times 3, so 6 minus 4 minus 6 is minus 2, so you obtain minus 2. You can also measure the length of vector. For this, use norm. For example, calculating the length of the vector 3.35 gives 5, which is the square root of 9 plus 16. For 2D arrays, you can calculate the length of specifying the axis. With axis is 1, we measure the norm in the direction where 0, 0, 0, 1 increase just as before. The norm of 3, 4 is 5. The square root of 9 plus 16. The norm of 1, 2 is square root of 1 plus 4, so which is root of 5. For 5, 12, it's the square root of 169, which is 13. So we obtain this value. We these vectors. Now let's return to the problem of multiple regression. To perform multiple regression, let's first create the explanatory variable. In this case, we have two explanatory variables that we will generate as random numbers with some variation. Then we will multiply them by beta here. Beta values. For example, we will use intercept of y multiply the first expansion variable by 2 and the second by 3. What we are doing here is calculation here is the calculation y is beta 0 plus beta 1 xy plus beta 2 x2, which we saw in the slides. This creates our objective variable synthetically. However, to make it more realistic, we add some noise to simulate real-world data. When calculating multiply regression, we need to create a matrix related to explanatory variable. We do this by creating a matrix where the first column contains all ones, the second column contains the first explanatory variable, and the third column contains the second explanatory variable. This can be done using NTV.column stack. Once we have X, we formula from the lecture materials, translating the table matrix products and the inverse matrices into Python notation to estimate beta. When we calculate this, we find that the value are close to the original here 1, 2, 3 that we started with. Before we move on the coefficient of determination, let's review simple regression. In simple regression, we prepare data calculation mean, calculate variance and covariance, and then determine beta 1 and beta 0. As we discussed at the beginning of this class or in the previous class, when working on in-class assignments, we had to copy and paste these linear repeatedly. While this is manageable, it can becomes tedious when handling data multiple times. So we want to find a way to consolidate this process. This is where functions becomes useful. What we want is a function that, when given x and y, returns beta 0 and beta 1. Let's talk about what functions are. As programs become more complex, you may want to reuse the same process multiple times. That's when you organize process into functions. In Python, function are defined using def here, short for definition. For example, here is a function. The scope of this function corresponds to the indented portion. You can create an indent by pressing the tab key. This defines a function called greet that requires variable called name. It can be used like this. Uh, Here, it can be used like this. When we provide a variable value to this part, it gets assigned to the name variable. So let's try. Let's try by Python tutor. So first, so Alice assigns to name as message is create hello Alice. So this is returned, giving us hello Alice as the output. If we want to change this to another name, like Bob, we just use greet Bob. So, so Bob is assigned to a name. A message is created by combine hello with Bob. This is returned to give us hello Bob as output. Okay. So arguments can also have a predetermined value. For example, functions can have not just one, but two arguments. Arguments with predetermined values are called default arguments. For instance, when we execute introduce Bob 30, this function is called with Bob assigned to name. Let's try Python tutor. So this function called with Bob assigned to name and age to 30 to age. The function processes this outputting name Bob age 30. If no arguments are specified, default arguments are used. John is used for name and 20 for age. There are default arguments. If Alice is specified, Alice is used for the name, and since age is not specified, the default argument 20 is used, resulting in name Alice age 20. In Python, you can return multiply values separated by comma. So here, for example, let's create a function that take arguments uh, a and b and returns a plus b and a times b. When executed, since there are two return values, we received them with two variables. When calc starts 3.5, 3.3 comma 4 is calculated, A becomes 3 and B becomes 4, resulting in 3 plus 4 is 7 and 7 times 4 is 12. These values 7 and 12 are returned. With received 7, indeed, like that. So return value with S receiving 7 and P receiving 12, and the results are output. You might be hearing about tuples for the first time, but they're used like list. The difference is that you can change elements after creation. Lists use square bracket, while tuples use uh, parentheses. Now that we have the two, let's create a function for. Okay, let's create a function for simple regression. We define a function called simple regress like this. There's a comment section that isn't necessary for functionality, but helps explain what the function does. Okay, back. The key part of this function is here. It receives x and y, calculate means, calculate variance and covariance, uh, computes beta 0 and beta 1, and finally returns beta 0 to beta 1. The process of defining x and y So the process of defining x and y, calculating means, calculating variance and covariance and so on can be simplified from 4 lines to just one. Uh, that's the power of function. In fact, we have been using functions like np.mean or along, which are already handling multiple processes behind the scene. Made us in one line thanks to the hard work of developers. So let's also create a function for the coefficient of determination. Since the coefficient of determination can be calculated using actual value and the predicted value, we compute the mean of actual value, calculate the total sum of square, calculate the square of the difference with predicted values, and perform the division to get the result. Uh, Okay, let's execute. Uh, when we actually run this, here's what happened this data. First, we provide a slope and the y-intercept. Then create random data for x. We calculate y by multiply uh, x by a, adding b, and then adding noise, resulting in the black dots. We can predict beta 0 and beta 1 using simple regression. Once we have beta 0 and beta 1, we can calculate the predicted values correspond to x. Now that we have both the actual data values and predicted values, we can calculate the coefficient of determination, which is 0.8, around 0.8. That's close to 1. On the other hand, let's intentionally use just random numbers. That is, let's make y completely independent of x using random numbers following a normal distribution. When we apply selection to this calculated predicted value using beta 0 and beta 1, and compute the coefficient of determination, we get 0.04, which is very close to 0. This concludes the code explanation. The rest is code for generating figures for the slide, which you can look at if you are interested in how the figure were created. But it's optional. It's just for reference. That's it. Okay, now please work on the in-class report for the last page.